Hello everyone. Today we are going to talk about the uh, machine learning performance boosting method under the AI 101 fundamental series. Okay, I am Dr. Egyaras Pandey and assistant professor at Kathmandu University and the AI program coordinator at this university. Uh, let's start from the machine learning training procedure first, and this is a supervised training method. Here we have a training data and the respective label. For example, if we are dealing with the classification problem, the cat and dog classification problem, then we have one cat image and the respective label, that is the cat given by the human expert. And in this way we have the large number of the data of the cat and the dog, right? And we fit this data and the respective label to the machine and try to adjust their parameters, right? Adjust their parameter that we call the machine learning. And after the machine training, we input some test data. That this is the some data which is not used in the training process, right? And in the new data, the model is already trained. That's why it should perform well to predict whether the data is cat or dog. In this case, if we are dealing with the cat and dog classification problem here. Okay, this is some machine learning process. And we already know that the machine should the model should be proper according to our problem complexity. For example, this is the underfitting case. Here the model is linear, but the data is more complex, or some problem is comparatively non-linear, right? That's why the linear boundary, the classification boundary, cannot distinguish these two classes well, and that's why we call this problem is a underfit case. Okay, and if we are trying to make our model more complex than our the problem, then it could be the case of the overfit. And here the model can perform well in the training process but not in the test process. That's why we try to maintain the optimal solution for our problem. Okay, so we already discussed that we need to balance our model within this region, within this white region, right? In the left side, this is the overfitting region, and the right side, this is the overfitting region, and in the left side, this is the underfitting region, right? So we need to balance our model to make the bias variance trade-off. Okay, and one of the method to make the to make our model more accurately predict on the data. One of the method is the validation set approach, which try to minimize the bias between the model prediction and its actual scenario, right? Actually, the how the model is biased from its actual solution. Okay, one of this model method is the validation set approach. In this method, we make some data. One is the validation data and another is the test data, and we try to participate all the data in the three sets, right? Here the 80% of the training data and the 10% could be the validation data, and the 10% could be the test data. And here the validation and test data is more like similar data, right? And we use this training data in the training process, right? To train our model. And after the training, after each epoch means if we feed all the data, all the training sample to our network for the training at a time, then we call it as the completion of one epoch, right? In each epoch we use the validation data to test our model, and if the model is performing well or reducing the loss, then we continuously try to minimize the loss. Otherwise we should adjust our the model or some label given on the training data, okay? And in this way the validation data try to control the model performance, or try to monitorize the model performance on the training data, right? This is one approach to 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 minimize the bias variance trade-off in machine learning. The another method is a leave one out cross validation. Here in this method is basically useful for the small data, right? And if we have the n number of the sample data for the whole data, and then we separate the one single sample as a validation data and other sample as a training data. And if we have the n data and we need to train the n model in this way, and finally all the prediction from the each model we aggregated and then decide the final decision, okay? This is one leave on out cross validation, but it is not feasible if we have the large number of data, right? If we have the millions of data, then I think this method is not proper. So the another way to handle such large data is a cross validation method, k-fold cross validation model. In this method we divide the data into different split, okay, different fold. Here this is the case of the 5-fold cross validation. Here we divide all the data into the 5-fold first, and each fold is a test sample at a time. And if we have the 5-fold here, we need to train the 5 model, right, at a time. And we can say that the blue data is the test data, and the white boxes is the data of used for the training, right? If we have the 5-fold cross validation, then we need to train the 5 model, and finally we aggregated all the performance from each model, and then make the average for the final decision, okay? This is somehow better than the this leave on out cross validation, but these two cross validation methods are basically used in machine learning if we have the small amount of training data, okay? And another is the subset selection method. In the subset selection method, and we have actually the large set of the data, okay, large set of the data, large set of the features. But as we know, the machine learning method have the limited amount of the parameters to train. So we only select the some features at a time, and we try to train our model and perform and evaluate the performance. And if the performance is acceptable, then we we select these features as the best features. Otherwise we iteratively select, and then up to this stopping criteria meet, okay? And this method improve the performance, model performance with limited parameters, and obviously reduce the complexity, and if we have the very limited number of the features, then it is very easy to interpret them, and also it reduces the overfittings. Okay. Another method is the ensemble method. In the ensemble method, rather than believe the just one model, we train the n number of the model in the same data, and after training in the test data, we take the prediction from all the model, and then make the either average or some kinds of the voting for the final decision, right? This is the more democratic model to make a decision on a test sample. And another is the hyperparameter tuning. In the neural network, we have the two things. One is the parameters. Generally, the parameters are the weight and bias, and which automatically updated during the training time by the neural networks, right? And in this training, actually we have the forward pass and backward pass. In the backward propagation, we already know it. In the backward propagation, we update the weight and the bias, and to make our prediction more similar to our ground truth, right? In this way, the parameter is updated, and these are the basically the weight and bias are the neural parameters on the neural network. That is the only the updatable things on the neural network. And the hyperparameter is those items which are set manually by the AI engineer, okay? And this could be the learning rate, optimization method, number of echo, activation function, right? And then if we are using the cross validation, k-fold cross validation, what is the number of k, like 5 or 10, okay? And then the gamma is the, if we are using the value activation function, then how much could be the what could be the value of the beta, right? And similarly, the number of iterations, then the size of the test case, and other things. These are some things that the AI engineer should manually adjust during the training time. And if we select these hyperparameter properly at the training time, then obviously our result could be very good. Okay, that's why the hyperparameter selection is the one way to improve the model performance. Okay, the one of the method to select the hyperparameter could be a grid search. In this search, we first make a pool of all the hyperparameter, then we manually set all the hyperparameter and check one by one. Okay, but this is not feasible if we are working on the large data set, right? It could be the very time consuming, right? And then in this case, the randomly we can select some hyperparameter, but here also some good hyperparameters could be missed by this random selection. And the another approach could be the genetic algorithm. In this genetic algorithm, we initialize all the hyperparameter as the initial population, and then we select the best hyperparameter and make them crossover mutation, and it means we evolve these hyperparameters and set our fitness function, whether the function is which one is the best, okay, which one is the best, which for classification, which model give you the best accuracy, or F1 score could be the fitness function. In this way, we iteratively select the best hyperparameters, and this could be the one method on the machine learning which can improve, which can help you to identify the best hyperparameter, and then obviously to get the best performance from your model. And that's it for today. And And if you have any query, you can contact us. And this is the end of this fundamental series. And next we will talk more about the machine learning approach. Machine learning approach. Thank you very much for the today. See you next week.